Okay, in this video we're going to consider more examples on integrating factors. If you haven't watched our videos on exact ODEs and integrating factors 1, I would advise that you first do that before you continue with this video. So in integrating factors 1, we just considered examples where the integrating factor was either a function of x only or a function of y only. Here we're going to look at examples where the integrating factor is a function of both x and y. And typically in this case, the integrating factor is going to be provided. Like in example 1 here, the question says prove that mu equal 1 over x squared y squared is an integrating factor of this ODE here. And then once that is proved, then we are going to use that integrating factor to solve the ODE. Okay, so if that function is an integrating factor of this ODE, then if we multiply by this ODE by mu, then we expect the resulting ODE to be exact. So let's see what happens when we multiply. So multiplying by mu gives so the first term is going to be 2x over y. Then this one is going to be y over x squared. So we're just dividing everything by x squared y squared. And then this one is just going to be 1 over x. And the last one is going to be x squared over y squared. So that's what our ODE is now going to become. So this is our new m, and this is our new n. Let's see what the derivative of m with respect to y is going to be. So derivative of this, derivative of 1 over y is negative 1 over y squared, and this term is going to give us 1 over x squared, because derivative of y is just going to be 1. Then derivative of n with respect to x, derivative of 1 over x is negative 1 over x squared. Derivative of x squared in the second term is 2x. And as you can see, my is equals to nx. Which shows that ODE is exact because my is equals to nx. So that proves the first part of the question. So remember, I wanted to prove that this function here is the integrating factor. Then for the second part, we are now going to want to solve this equation using this information. Okay, so we have seen that if the equation is exact, it means there exist some function f such that the derivative of f with respect to x is going to be 2x over y excuse me, minus y over x squared. At the same time, derivative of f with respect to y is going to be our n 1 over x minus y squared over x squared. If we integrate that first one with respect to x partially, we're going to have x squared over y plus y over x. So here we've got integral of 2x is x squared. Integral of minus 1 over x squared is minus 1 over x. So the sign changes. Then this is going to be plus some function of y. Okay. Then if we differentiate this now partially with respect to y, the first term is going to give us negative x squared over y squared. Second term going to give us 1 over x, and then this is going to be plus derivative of phi. So if we compare these two, what it means is that phi prime is equal to 0, and so phi is just a constant. Okay, so therefore the solution is going to be so it's just going to be our f here, and then in the place of phi we're going to plug in a constant. So we're going to have x squared over y plus y over x plus k equal to 0. So this is our general solution. All right, so that's the solution of that equation. So let's look at another example. All right, in this example, we are going to be given an ODE like this one, and then we are given an integrating factor, or at least its functional form, like here, x to the power m, y to the power n. M and n are real numbers, so we need to show that this ODE has an integrating factor of this form. So basically we need to find the values of m and n, and then once that is done, we're going to use that to solve the equation. In part B is the same scenario, but the powers are the same here. Okay, so the first thing I want to do is to multiply this ODE by this function here, and then we're going to see how the values of m and n are determined. Okay, so in A, multiplying the ODE by mu. All right, so this is what we're going to have. So the equation is going to be 4x to the power m plus 1, y to the power n plus 2, plus 3x to the power m, y to the power n plus 1 dx the second term is going to be 3x to the power m plus 2 y to the power n plus 1 plus 2x to the power m plus 1 y to the power n dy is equal to 0. And then from here, so the derivative of m with respect to y, so here we're going to multiply by n plus 2 x to the power m plus 1 y to the power n plus 1, going to subtract 1. For the second term, we're going to multiply by n plus 1, 3n plus 1 x to the power m y to the power n, and then derivative of n with respect to x. So in the first term, we're going to multiply by m plus 2. The second term, we're going to multiply by m plus 1. So here m plus 2 x to the power m plus 1, we subtract 1 from this power. This one remains the same. And then 2 into m plus 1 x to the power n y to the power x to the power m y to the power n. So for these to be equal, so for my to be equal to nx, we must have so for this to be equal, you can see that these powers are the same, so we need this coefficient to be equal to this one and this coefficient to be equal to that one. So we need for n plus 8 to be equal to 3m plus 6. We need 3n plus 3 to be equal to 2m plus 2. So it's a linear simultaneous system of equations. Solving this, we get m is 2 and n is 1. Okay, so then if we go back to this ODE, so the ODE is going to become so the ODE is going to become 4x cubed y cubed plus 3x squared y squared dx 3x to the power 4 y squared 2x to the power 3y dy equal to 0. And then we can solve this as usual, or maybe let's go through the steps. So this is going to be exact, so it means fy is going to be equal to 4x cubed y cubed plus 3x squared y squared. If we integrate this, then this is going to be x to the power 4 y cubed plus x to the power 3 y squared plus phi of y. if we do, sorry, this is fx actually, so that was integrating with respect to x. Okay, then if we differentiate this now with respect to y, it's going to give us 3x to the power 4 y squared plus 2x cubed y plus 5 prime. Then we're going to compare this with that. Okay, so we compare these two, and then that is going to tell us that 5 prime is actually 0, which means phi is a constant. So the solution is simply going to be x to the power 4 y cubed plus x cubed y squared plus k is equal to 0. Okay, we are not going to give you a chance to have a go at the second example here. We just want to have a go at this part B. Pause the video, and then when you press play, then you can compare with our solution. All right, so we're now going to show you our solution to this part B. Okay, so if I multiply the ODE by nu, this is the equation we're going to get. Then if we differentiate the first term with respect to y, we get that. If we differentiate the second term with respect to y, we get that. Now, for these two to be equal, you can see that the first terms are the same. So we just need this one to be 0. This one can be 0 if n minus 3 is 0. So we need n to be 3. And then if n is 3, the ODE becomes like this. Okay. So since now this is exact, it means there is a function f which is such that its derivative with respect to x is equal to that term. If we integrate this with respect to x, we get x to the power 4y to the power 4 over 4 plus a function of y. We differentiate this with respect to y, we get this. Then we're going to compare with that. You can see that this term tallies up. So 5 prime must be equal to negative 14y to the power 6. Then if we integrate this, we get that phi is k minus 2y to the power of 7. Then if we take this and plug it in here and equate to 0, so that gives our solution there. All right, thank you very much. If you hopefully found the video helpful, if you did, please do subscribe so that you can get notified whenever we post new stuff. Thank you.